Hello again, everyone. So in this video, we're again going to be talking about a special type of vector subspace. So in the previous video, we talked about the zero vector subspace, and we saw why it was interesting, because it was the only vector subspace that only contained one element, and that actually was a vector subspace, because otherwise it wouldn't be a vector subspace, as it would fail the first condition. Okay, so when you think about it, the zero vector subspace is kind of like the smallest possible vector subspace. Vector subspace of a vector space V. Okay, let's say V is a vector space. Okay, and I say smallest possible in the loosest kind of way, because we really have to talk about cardinality and the size of the set and all that, and that's really beyond the scope of linear algebra typically. You usually see that in set theory classes, and that's not really the goal of this video. Really, what I'm trying to say is it's the smallest possible vector subspace of V, in the sense that you can't have a vector subspace that has nothing, right? You like you can't say W is the empty set, because this is actually the empty set. This is called the empty set, but it would of course not it wouldn't satisfy any of the conditions, because first of all, the zero vector doesn't belong to it. Okay, so already it would fail condition 1. Okay, so what am I getting at with this? So we can say that the zero vector is the smallest possible vector subspace of V, but we can sort of think of it the other way. What is the largest? What is the largest possible vector subspace? Vector subspace of our vector space V. Okay, so think about it. Like, we had one element for the smallest vector subspace. So how many elements would you really need for you to have the largest possible vector subspace? Do you need to know how many elements V has? Do you have to number them? Well, it turns out that the answer is actually much more intuitive than you might think. So if you want to think about the largest possible vector subspace, well, we know that a subspace is a subset of V. Okay, but there's nothing from preventing us to say that V is a subset of itself, because you can always say that in set theory. You can always say that if you have a set, so suppose you have a set V, what does it mean for something to be a subset of something else? It means that for all x in V, x is in V. And this is of course true. It's trivial, because whatever is in V is going to be in V, is just stating the obvious. But this tells us that V is a subset of V, and because we have the properties of a vector space defined by its axioms, we can already say that we have a vector subspace. And I'm going to tell you why. Is because when defining a vector space, we always start with two basic definitions. We always have two basic definitions. And I talked about this in my videos about vector spaces, but if you don't want to bother going back to them, which I could understand, well, the first basic definition is vector addition. Vector addition. And vector addition just says that if you have two vectors, U and V, right? V is now a vector space, and you add them together, then they'll still be in V. Or you can think of this as sort of a closure under addition. And then the second condition is that we have a scalar, not a condition, a definition. We have a scalar multiplication that's defined as, if we have a scalar c and f, typically it's going to be r in this case, because we're not dealing with complex right now, and we have a u in v, then if we do c scalar multiplied u, then by definition, we're given this by definition in the basic properties of a vector space. By definition, this scalar multiplication will also belong to v. Okay, so remember what we need for something to be a subspace. For something to be a subspace, we need, the first thing is we need the zero vector. The second thing is we need the closure under addition. And the third thing is we need CU, scalar multiplication. Of course, I'm writing this very, very broadly and very informally, but you would, of course, need to write the definition for each of these. But it looks like, sorry about that, someone called the house, because we have a house. Okay, so it looks like CU is going to work because we have this property right here. Because remember, what we're dealing with is V being a subspace of itself, basically. So this is what it means. We're trying to see if V is a subspace of itself. Okay, so is this true? Well, CU definitely works because scalar multiplying U just gives you something that's in V. And that's what we're dealing with. We're dealing with V as a subspace. Okay? And then we have the vector addition. That also works because of this. Now, the only pickle is the zero vector. Okay? But the zero vector comes from one of the axioms of a vector space. So if you recall one of the axioms, of vector spaces. The axioms of vector spaces. So in my definition, we had axiom 3 that stated an existence proof for the zero vector. It said that there exists a zero vector. So this is what we call the zero vector, such that if u belongs to V, then u plus the zero vector is equal u. Okay, and that's how the zero vector was defined. But so that means that if there exists a zero vector, that means that the zero vector does belong to V. So this is also checked. So in fact, V, so what we can conclude from this, so our conclusion here is that V is a subspace of itself. Now this might seem a bit arbitrary and a bit abstract, because I'm dealing with V and not an actual vector space. But now let's think about let me give you an example of a real vector space. So suppose we have V as R3. Okay? So V is all of R3. In other words, it's any of the vectors that look like A, B, C. So any 3-component vector that looks like A, B, C, such that A, B, and C belong to the real numbers. So the first condition was that the zero vector belonged to V. Well, of course, this is true. This is true if we make A equal to B equal to C equal to 0, because 0 belongs to the real numbers. Okay? So then we would have the 0, 0, 0, which is the zero vector. Okay? And then the second one is closure and addition. Well, if you add two vectors A1, B1, C1 to A2, B2, C2, then you're still going to get a 3-component vector. Okay, and that 3-component vector has to belong to R3. Similarly, for the third condition, if I have a scalar C that belongs to R, and I just scalar multiply A, B, and C, it doesn't matter it doesn't really matter, like we don't really care about the operation in here. The only thing we care about is, does it still look, so does it look like it belongs to R3? And yes, it does, because it has 3 components, and all of them belong to R. Okay, so that's how you sort of think about the largest possible subspace of a vector space. It's actually the vector space itself.